Okay, this is exercise 2.2, types of stationary points. Now, in this exercise, we're going to be looking at 3 types of stationary points. Okay, what defines a stationary point is that at some point on the curve, you will have a gradient of 0. So if we look at the gradient of the curve here, it's negative. So this is a negative gradient, and that's indicated by the first derivative. So here I've got a negative gradient. So on this left-hand side of this curve, the first derivative, or the gradient, is negative, so it's less than 0. At this point here, I have a 0 gradient. So the first derivative equals 0. And on this side of the curve, this is a positive gradient, so first derivative is greater than 0. Now that's a minimum. We can see that we have a minimum point on the curve here. So this is the minimum down here. Down here, we can see that the gradient changes from negative to 0 to positive. Now this is really important because when you test to see whether you've got a minimum turning point or not a bit later, we'll be looking at the gradient on either side of that minimum. So the minimum is here, where the gradient is 0. Okay, but on either side of the minimum, you've either got a positive or a negative gradient. So we've got negative gradient, 0 gradient, positive gradient. That gives us a minimum. Here with a maximum, here's my maximum turning point up here. And at the maximum, the first derivative is 0. But on either side, on the left-hand side of the maximum, we have a positive gradient. So f dash x is greater than 0 on the left. And on this right-hand side of the maximum, I've got a negative gradient. So f dash x is less than 0. And so later, with some questions, if you're testing whether it's a maximum, you'll find your stationary point there, and then you'll look at the gradient on the left-hand side and on the right-hand side of that stationary point to determine whether it's a maximum or a minimum. Now with horizontal inflections, this is an inflection here, and we can see at this very point here in the middle that the gradient of the curve is 0, right? It's flat. Also here, so here we're coming up to the inflection there. Here the gradient's positive, 0 gradient, and also coming up here, gradient's positive. So with an inflection, you've got positive gradient, then you've got 0 gradient, then you've got positive gradient with this type of inflection. Then you've also got this type of horizontal inflection. So here, gradient of tangent to curve is 0. However, here, down here, I've got a negative gradient, and down here, I've also got a negative gradient. So if you've got negative gradient, 0 gradient, negative gradient, so f dash x is less than 0 there, and here f dash x is less than 0. Okay, so if you've got negative gradient, 0 gradient, negative gradient, you've got a horizontal inflection. Also, if you've got positive gradient, 0 gradient, positive gradient, you've also got a horizontal inflection. Now, I'm just going to look at a couple of questions in exercise 2.2. First one we're going to look at is question 10. Question 10, find the stationary points on the curve function of x equals x to the power of 4 minus 2x squared minus 3. So, we know that at stationary points, as we've looked at before, and I'll just write this up in the heading, it is where the gradient of the curve equals 0. So the first derivative has to equal 0 at stationary points. So let's look at the first derivative here. So function of x is x to the power of 4 minus 2x squared minus 3. So f dash x, the first derivative, is 4x cubed minus 4x. Okay? Now, at stationary points, so for stationary points, f dash x equals 0. So we will put this function equal to 0, or this first derivative equal to 0. We need to factorise what our highest common factor will be 4x. We're left with x squared minus 1 equals 0. So factorising this difference of 2 squares here, we've got 4x bracket x minus 1, x plus 1 equals 0. So therefore, we have 3 solutions here, that x is 0, x equals 1, or x equals negative 1. So we've got 3 stationary points, in other words, 3 points where the first derivative equals 0. Now, we need to work out the corresponding y value. So when x is 0, I'm just going to put the corresponding y values. When x is 0, putting it back into the original function, y is 0 minus 0 minus 3, so it's negative 3. So 0, negative 3 is a stationary point. When x is 1, you've got 1 to the power of 4, which is 1 minus 2 times 1 is 1. So it's 1 minus 2, which is -1, minus 3 is -4. So our other second stationary point is 1, -4. And our last stationary point, well, if you're squaring a negative or if you're raising a negative to the power of 4, you'll get positive answer anyway. You're actually going to get the same answer as you did for when y is 1, so you'll get y is -4. So we've got 3 stationary points at 0, 3, 1, 4, -4, and -1, -4. So now what we're going to do is draw up, look at the nature of the curve, look at the gradient of the curve on either side of all of these stationary points. But we've got to be very careful of the points we choose, because, for example, if we're examining this point where x is 0, we can't go beyond 1 or -1 on either side. So we know we've got stationary points at 0, -1, and 1. So we're going to be testing a point on either side of the -1, and we're going to be testing a point on either side of the 0. Why not test a half, -1/2 and a half? So that way when you test this point, you're testing it for the 0, but it's also going to be relevant to the -1. So maybe we should choose the points -1/2, sorry, -1/2, a half, 1.5, and -1.5. Okay, so we're going to do, I can probably fit them over here, so I'm just going to do them over here. So let's look at our first point when, let's look at this stationary point here. When x is -1, let's look at the gradient. Now it's really important that you label this properly. This is f dashed x. I know that when x is -1, the gradient of the curve is 0, so I'm going to look at -1.5 and -0.5. So you're going to need your calculator. So just make sure that you're substituting these x values not into the function of x curve, but into the first derivative. So we need -1.5 substituted into both these x's here. So when we substitute into 4x cubed minus 4x, we get -7.5. When you substitute it into the next curve, the next number into this, we get positive 1.5. So looking at this first stationary point, which is when x is -1, we've got, if you look at this gradient here, it's negative, then we've got 0 gradient, then we've got a positive gradient. So therefore, the point -1, -4 is a minimum turning point. Okay, we can look at the next point as well. So I'm going to look at the next point, which is 0. So 0, -1/2, and +1/2. We've already got this -1/2 done here, so that's positive 1.5. Now we need to do the first derivative for +1/2. So it will be 4 times +1/2 cubed, so 4 times 0.5 cubed minus 4 times 0.5 gives us -1.5. We know that when x is 0, the gradient's 0 as well. So therefore we've got positive gradient, 0 gradient, negative gradient. So therefore the point 0, -3, we know the point is 0, -3, is a maximum turning point. And now for the last point. Okay, now just notice when x was 1/2, the first derivative was -1.5. So as I test this last stationary point, which is at x is 1, so the points on either side will be 1/2 and 1.5. When x was 1/2, we got -1.5, so we've got negative gradient, 0 gradient, and now we can substitute 1.5 into the equation. So 4 times 1.5 cubed minus 4 times 1.5, we get 7.5. So that's positive gradient. So therefore this is also a minimum turning point. Okay, so therefore we've got those 3 turning points. That exercise, question 14, a curve has first derivative equal to x bracket x plus 1. So this first derivative has already been factorised. For what values of x does this curve have stationary points, and what type of stationary points are they? We know that for stationary points that the first derivative is equal to 0. So we know our first derivative is x bracket x plus 1 equals 0. Therefore, x equals 0, x equals -1. There are stationary points at, so therefore stat points at x equals 0 and x is -1. And we actually can't work out what the y values are because we don't have the original curve, but we can look at points on either side of that stationary, at either side of those stationary points to determine the gradient on either side of the stationary points. So remember, our two stationary points are at 0 and the other one's at -1. So at 0, just looking at either side of 0, I'm going to go -0.5 and +0.5. And on either side of -1, I've got -1.5 and -0.5. So this value here will be in common. Okay, so we just put these values there into the equation for the first derivative. So if x is -0.5, we've got -0.5 times -0.5 plus 1. 1 plus -0.5 is 0.5. So it's 0.5 times -0.5, which is -0.25. We know that when x is 0, f dash x is 0, that's what was determined there. And when x is +0.5, we've got 1/2 times 1 plus 1/2, which is 0.5 times 1.5, and we get a positive gradient here. So therefore, we've got negative gradient, 0 gradient, positive gradient. Now for this curve here, we know that when x is -1/2, we had -0.25. When x is -1, we know that the first derivative, make sure you put here, first derivative is 0. And for the last point, -1.5 times -1.5 plus 1. -1.5 plus 1 is -0.5 times -1.5. A negative times a negative is a positive, but we're just going to work out the value anyway. And the value is +0.75. So therefore, we've got a positive gradient, a 0 gradient, and then a negative gradient. So therefore, we have a minimum turning point at x equals 0, and we have a maximum turning point at x equals -1. Looking at question 20a, differentiate x, this function here. Now this is, we will use the product rule because we have two functions in x. There's a function in x here and there's a function in x there. So we're going to use product rule. Now u is x and u dash is 1. V is the square root of 3,600 minus x squared, which can be written as 3,600 minus x squared to the power of 1/2. And v dash is, just differentiating that, bringing that half to the front, 1/2 times 3,600 minus x squared, decreasing this power by 1, so 1/2 minus 1 is -1/2 times, we need to differentiate what is inside as well, times -2x. So therefore, multiplying the half by -2x, we've got -x bracket, and this will just be 3,600 minus x squared to the -1/2. Now, I'm not going to write that as a square root at the moment. I'm just going to keep it like that. Or actually, I could, if I wanted to write it as -x over the square root of 3,600 minus x squared. To the power of -1/2 brings that to the denominator, and 1/2 is square root. So that is v dash. Now, I'll have to do this bit on the next page. Find any stationary points for that curve. So I'm just going to keep going with this differentiation. So a dash, or I can write dA dx, is u v dash plus v u dash. So u is x, v dash, I can use either form here. I'm going to use this form up here, this one here, not written as the square root. So it's u times -x bracket 3,600 minus x squared to the -1/2 plus v, I'm going to use this form of v, the index form, 3,600 minus x squared to the 1/2 times u dash is 1. The reason I'm using these forms with indices is that I can pull out the common factor, because we're going to have to put a dash in part B, we're going to have to put a dash equal to 0 to find the stationary points. So it really needs to be in a factorized form. So, okay, looking at the highest common factor between 3,600 minus x squared to the -1/2 and that same term to the +1/2, the lowest common factor is 3,600 minus x squared to the power of negative a half, because that is a smaller index than positive a half. And if that's pulled out as a common factor, we're left with negative x squared plus 3,600 minus x squared to the power of positive 1. Because if you multiply 3,600 minus x squared to the power of negative a half by 3,600 minus x squared to the power of positive 1, the bases are the same. If you add the indexes, you get positive a half. So therefore, we've got 3,600 minus x squared to the negative a half. And expanding this, we've got negative x squared plus 3,600 minus x squared. So we've got 3,600 minus 2x squared. Okay, that's the first derivative. Part B, to find any stationary points for that curve and determine their nature. So we're just going to put that expression there equal to 0 and solve. So therefore, for stationary points, a dash equals 0. In other words, 3,600 minus x squared to the power of negative a half times, well, I'll just put bracket, 3,600 minus 2x squared equals 0. Now I'm going to write that now as a fraction. So 3,600 minus 2x squared over the square root of 3,600 minus x squared equals 0. That is what that is equivalent to. Now for this expression to equal 0, the denominator cannot equal 0. So therefore 3,600 minus 2x squared must equal 0. As this denominator, you can even say that you're going to do a half cross multiply, okay? Multiply both sides by that expression. But the truth is, the fact is that for something divided by something else to equal 0, only the numerator can equal 0. The denominator can never equal 0. So it's just you need to just put the numerator equal to 0. Or you can multiply both sides by square root of 3,600 minus x squared. That will always be positive because it's square root of that. And that'll just leave that the numerator here is equal to 0. And factorising that out, we can divide by 2. We would get 1,800 minus x squared equals 0. We can just solve by saying x squared is positive 1,800, therefore x is plus or minus the square root of 1,800. They've just asked for this to 1 decimal place, okay? So to 1 decimal place, this is x is approximately equal to plus or minus 42.4. So square root of 1,800 or 1,800 is to 1 decimal place is 42.4. Now we need to look at the nature of the stationary points. So when x is 42.4, we're looking at a dash. We know that a dash is 0 when x is 42.4. And we can look at a point on either side. You can go 43 and 42 if you want. That's fine, okay? So when x is 42, we need to substitute into the equation for the first derivative. And I'll just write down what that equation here is so that you can see it. It's just a dash, actually it's this one up here, which is actually that as well. A dash is 3,600 minus 2x squared over the square root of 3,600 minus x squared. So we can just substitute it into that. That's what a dash is here. And so is this, just this written in surd form as opposed to index form. Okay, so I'm just going to pause the video while I calculate that, substituting 42 into the x there and there as well. So substituting in those values, when I substitute in 42, we get positive 1.68 in the first derivative, and substituting 43 in, we get negative 2.34. So we've got a positive gradient approaching that stationary point, then 0 gradient at the stationary point, and then negative gradient. Therefore, we have a maximum turning point. I'll just put turning point there at, actually I'll write it out. Maximum turning point at x equals 42.4. Actually, we can work out what the value is. So we can work out what the y value is, or the a value is as well. So when x is 42.4, Actually, I'm not going to use the 42.4 when I'm working out the value of A, because you're substituting into, we'll be substituting into the original value for A, which is x times 3,600 minus x squared. So when x is approximately 42.4, but we know that the exact value was square root of 1,800, we get that A is square root of 1,800 times the square root of 3,600 minus the square root of 1,800 squared, which is just the square root of 1,800 times the square root of, this will be 3,600 minus square root of 1,800 squared is just 1,800, so it's the square root of 1,800 as well. So square root of 1,800 times square root of 1,800 is square root of 1,800 squared, which is 1,800. Okay, so therefore maximum turning point at 42.4, 1,800. Okay. Now, the other turning point, x, we're looking at negative 42.4. Just be careful, the term lower than negative 42.4 would be negative 43, and higher would be negative 42. Just look at what we're substituting into. The x is going to be squared, both on the numerator and the denominator. So whatever value you got for 43 up here, you're going to get the same value for negative 43. So we're going to get the negative 2.34 for your a dash there. We know that the first derivative is 0 there, and for negative 42 we're actually going to get the same value as 42 when it was substituted there, which is positive 1.68. So therefore we've got negative gradient, 0 gradient, positive. Therefore we've got a minimum. So we've got a minimum turning point at, and again, if I substitute, x is negative square root of 1,800 into this, so just do that. A is negative square root of 1,800 times the square root of 3,600 minus the square root of, actually x squared will be negative square root 1,800 squared. The square, there's no negative under the square root, so it will be negative square root of 1,800. Here we've got 3,600 minus negative square root 1,800 squared is positive square root, is positive 1,800. So it'll just be 3,600 minus 1,800, which is going to be the square root of 1,800. Okay, so we've got negative root 1,800 times root 1,800 is going to be negative 1,800. Okay, so therefore you've got the minimum turning point, so just be careful here. This will be 3,600 minus square root of negative, square of negative square root of 1,800 squared. You square the negative, you get the positive. Square root and squared cancel, you will get positive 1,800 for this whole thing. So it'll still be just 3,600 minus 1,800, which is the square root of 1,800, all right? So negative root times the positive root will just be negative 1,800. So minimum turning point at negative 42.4, negative 1,800. And that's the end of question 20.